And apparently he's like no slouch either. Like, apparently he's like really, really good. So this is a strong baseline. Yeah, it's pretty good. So a couple things that are interesting here. So first of all, sometimes the neural net is doing just slightly better than humans, but sometimes, like in Breakout, it's like unreasonably better. Like there's no way you could play Breakout nearly as well as the video game agent.
So what's the best linear learner? That isn't a human, is it?
So this, I think, what this says, actually I can't remember, maybe someone else knows. Maybe, like, instead of a convolutional neural net here, just like some linear, just like do a linear function full of pixels, something like that. I'm actually not sure. Yeah, so really cool. So a couple of other things that are interesting about this. This game here
Linear learner was the best.
vexed the community for many, many years. In fact, it's an active topic of research right now. It's called Montezuma's Revenge. So this is this video game. It's like one of those pathological games, kind of like Flappy Bird, where everything kills you, and it's super frustrating. So there's a couple of reasons that their algorithm didn't do well on this game. The big one is reward sparsity. So like nothing gives you rewards, or it's like you have to go through like 7 different screens before you get your first reward. And as a reason, but all this stuff kills you. And so what the agent quickly learns is to just like go left and give up. Like, I guess nothing I can do. Although actually, and my friends were telling me too that there was this funny failure mode at the beginning of these games where they learned that if you pause the game right at the beginning, then you never died. That's right. So the agent learned. Pause it. But it didn't give any positive reward either. Yeah. So reward sparsity.
Maximum
The fact
expected
that it
utility
takes
is
so
0
long
pause,
to
right?
get any positive reward, that's a big problem for these methods. And you have to be clever about, and you have to introduce
Don't
new
let it pause.
concepts. So usually, the way that the first experience database is generated is with random actions. So your behavior policy is just random. And the cool thing about that is you sort of explore all the controls. The bad thing is the probability that you'll somehow randomly do random actions and make it through all 7 screens to get your first reward is like 0. There's no way. There's no way it's going to happen if you do it randomly. So you have to be much more careful and directed about your exploration. Yeah, good.
So this is kind of a practical question. Do you know what the cost was to train this agent in terms of like
Let's see, do we have a learning curve?
electricity and the
Yeah, in terms of electricity.
and all that?
Yeah, so I don't have the learning curve here in this presentation, but I have seen it, and it's tens of millions of games. So on the order, however fast you can do that, I don't know, it's a couple days usually.
I'm just curious. We talked about like the brute force of that one paper, and I was wondering if there's like a
Yeah,
a
it is
problem
similar.
with this.
It is definitely similar. So I think as exciting as it is, and this made a big splash when it came out. Everyone's like, oh yeah, I solved Atari. As exciting as it is, it's clear that humans don't need 10 million experiences with a video game in order to achieve good performance. So we are able to extract a lot more information. In fact, we did this experiment in my lab. I had one student, he said, how much data do you even need from a game before you pretty much know how to play it? And the answer is 1 screenshot. Like, I can show you a screenshot of a game, and you can pretty much say, oh yeah, like, that looks like your life meter. I bet those are the points. I bet that's you. I bet those are the enemies. That looks like a power-up. I pretty much got it. Like, I bet if I push up, that's going to go up. I bet if I push left, that's going to go left. And you pretty much got it. Like, then as soon as you play for like 30 seconds, all of your uncertainty goes away. I mean, so real, but then it's just like figuring out the strategy and muscle memory, but we sort of get the game mechanics super quickly. Now that's because we have awesome like prior knowledge, which I think is a huge difference. Here we're training this stuff tabula rasa. It does not know what a pixel is, let alone what an enemy is, let alone what a mothership is. You know, so it has to learn all of that. Go ahead.
So should we have a baseline where we put like toddlers?
Yeah, that's a good question. Yeah, what would like a not super strong DeepMind expert look like?
The worst.
A cat? You have to sometimes incentivize the cat.
Wake up for that.
Dispense a treat. Oh, it's just like Pavlov's dog.
That's amazing. That is amazing.
Except Marissa's cat. Yeah, that'd be interesting. Yeah. I'm not sure. That'd be interesting.
Just really quickly, for these games, were they actually using a reward that was like from the screen, and this not only learned how to play the game, it learned how to view its own reward?
No. So the reward has been extracted.
Okay.
Like part of the simulator did that for them.
Okay.
And in fact, apparently, it's not nearly as hard as you might think. There was a convention among Atari 2600 programmers, like a certain register representative score.
Got it.
So would it be possible to train a very large kind of general neural net over several different games?
Yeah,
And you
good
think it
question.
would-
Right, so in this case, every game had its own neural net
Yeah.
trained, right? Is it possible to train one agent to rule them all?
Yeah.
And the answer is yes-ish. So it does not seem to be possible to train one algorithm to play all of these games better than if you trained on one specific
But-
game. But
My-
the question is, can you then maybe like transfer? Like, so you train on 30 of the games, and can you learn the other 10 games faster? And the answer is unknown. So that is an active area of research. It's called transfer learning, and it is yet a different slice through machine learning space. Yeah, so fun stuff. There's a lot of interesting questions here, and a lot of interesting possible extensions. This is the article. You can actually download the source code. It's been re-implemented a million times. Okay, so this is basic Q-learning, sort of Q-learning plus deep neural nets, plus a few tricks to stabilize them. There's been several improvements. So since then, and actually these slides are old, there's been several improvements even since these slides were created. Double DQN tries to get rid of this, like there's this bias, because you have this max in the Bellman equations, just an empirical thing is that max tends to, it's not robust to outliers. And so you get this bias, kind of, if you estimate things too high. So double DQN introduces yet another weights or something, like they do this funny little thing here, and that compensates for it. Prioritize replay says, let's not treat all of our experience the same. We'll treat what we think the most important experience is. We'll sample that more frequently. So the stuff we really had a hard time with, let's sample that more. The stuff that was easier, we'll sample that less. And then the dueling network I thought was really interesting. So you can think of a Q value as having two terms. There's the value of being in a state, and then there's the value of the action in that state. And you can kind of imagine that for certain states, it doesn't matter what you do, like it's just a bad state. But for other states, maybe it's highly dependent on what you do. So for example, in a driving game, if you're driving along and you're about to get in a collision, it might not matter what your action is. Like the value of that state's just going to be close to 0 or negative or whatever it is. But and so what you can do is you can split the network into a state-dependent part and an action-dependent part, learn both of them, and this turns out to work surprisingly well, better than other things. And you can then do things like sensitivity analysis to ask which pixels were most responsible for the value and which pixels were most responsible for the action. And you can tell what the network was looking for in the pixels. And it learns that, oh, I can control these pixels, but I can't control these pixels. Which I think is a neat result just of factoring this in a slightly different way. And then there's a thing called the rainbow DQN, which takes all of these things and puts them all together into one algorithm that does everything, and it is actually one of the currently state-of-the-art approaches. Take every good idea. Okay, so we will end there, and we'll pick it back up again on Friday. So have a great day.